This is a thin lens that is shown. We are going to place an object over here. So let me do that right now. So let us say this is our object. So this object is at a distance u from the lens. So this is the point which is the central point of the lens, and we are going to measure the distance from the central point. Now this lens happens to be a thin lens. So because it is a thin lens, this point and this point, let us say the points P1, P2 and P3 are considered to be very close to each other. So the object distance u can be from the point P1, P2 or P3. So from all the 3 points, the object distance u is going to be considered to be the same. So this object is forming an image at a distance v. We are assuming the image to be erect as of this example. So the image is actually inverted, then we will automatically get the value of the magnification to be negative, and hence we will automatically find that the image is inverted. So without loss of generality, we can assume that as of now the image is erect. So we would like to derive something called as the Lensmaker's equation, which is essentially the relation between u, v and the focal length of the lens. For deriving it, we need to apply the curved surface refraction formula twice. So what we have to essentially do is we have to understand that there are two surfaces over here. This is the first surface and this is the second surface. So we would like to write down what are the radii of the two surfaces. So this is the first surface whose radius is, let's say, r1. This is the second surface whose radius is r2. According to our sign convention, all directions in the parallel direction to the incident ray are to be considered as positive, and all directions opposite to the incident ray are to be considered as negative. So we can thenceforth see that all distances are to be measured from the pole, which is this particular line or this particular point. So we can say that the distance measured from the polar plane, which to elucidate is this plane. So this distance r2 is being measured opposite to the incident light, because the direction of incident light is so. So since r2 is being measured opposite to the incident light, we are going to take r2 as negative. So r2 will be negative over here. Now let's try to apply the curved surface refraction formula. It's mu2 by v. So first we are applying it at this surface, the left hand side curved surface. So as far as the left hand side curved surface goes, what we need to understand is the fact that the first image that will be formed by the left hand side curved surface will not be the final image. So let us say this is the object right over here. The first image that will be formed will be called as image 1 with an image distance of v1. Now this first image is going to serve as an object for the second surface, such that the second surface will form its final image. So this is the second surface, and let us say this is the first image v1. Alright, so this first image v1 will act as the object for the second surface. So mu2, so this is mu2 and this is mu1. Okay, so this is also mu1. So there are two mediums here. One is the medium that is outside the lens and one is the medium of the lens. So the medium of the lens is considered to be mu2 as a refractive index, and the medium that is outside the lens has a refractive index of mu1. So mu2 by v1, the first image, minus mu1 upon u. So here u has already been taken to be negative, is equal to mu2 minus mu1 upon r. So r1 is positive, so we just leave it like that. R1 happens to be positive. Now this v1 will act as the object for the second surface. So right now we analyze this. This was r1. So now here this is r2. Okay. So here we are going to get mu1 upon the final image v minus mu2 upon v1 is equal to mu1 minus mu2 upon the radius of curvature r2. So note that even though we know that r2 is negative and u is negative, we will use the fact that r2 is negative and u is negative when we substitute it in questions with numerical values. Here we also know that in most cases the image that is formed is inverted, but here we assume everything to be positive and we just take the values in terms of symbols at the face value. So we are not implicitly expressing things in terms of sign over here, because when we substitute the numerical value while solving numericals, we are going to be utilizing the sign. So this is equation 1, this is equation 2. Note that I have not made u negative over here or r2 negative over here, even though we know that both u and r2 are negative, because the incident ray is traveling opposite to the measurement of u and r2, because u is also being measured like so. So it's opposite to the incident ray, but still we are not utilizing them like that in the formula that we have derived, because we will use it with the sign when we are substituting the value while solving numericals, and hence we'll get an output or the final answer also along with the sign. So like we said, this is equation 1 and this is equation 2. When we add these two equations, we get mu2 by v1 and mu2 by v1 will get cancelled, that is apparent. So we'll get mu1 upon v minus mu1 upon u is equal to, now here what we do is, instead of writing this as it is, what we do is we insert a negative sign over here. So I am just writing it down over here. This is a negative sign over here, and we'll write mu2 minus mu1, because we would like to take this bracket common outside. So mu1 by v minus mu1 by u is equal to mu2 minus mu1 into bracket 1 upon r1 minus 1 upon r2. So now what we do is we divide the entire equation by mu1 and thus get 1 upon v minus 1 upon u is equal to mu2 by mu1 minus 1 into 1 upon r1 minus 1 upon r2. Now this term that we have obtained on the right hand side is nothing but the inverse of the focal length of the lens. So this particular equation is called as the lens maker's equation. This is a particularly important equation that the student should remember pretty much by heart. So this is the lens maker's equation. Most often the lens maker's equation is also written as one upon v minus 1 upon u is equal to 1 upon f. Note that we have to use the sign convention on this lens maker's equation while solving the numericals. Okay, So why is the sign convention not used while deriving? Because while deriving we never know, the length might be something like this. So for this lens both the radii are negative. The lens might be something like this. So for this particular lens, in the sense in which the incident ray is going in this particular diagram, both the radii can be considered to be positive. So we never know what kind of lens we would encounter. Okay, sometimes we would encounter this kind of a lens for which the situation would be opposite compared to the lens that we have used to derive. So for example, this radii will be negative and this radii will be positive. So it's always best to be independent of the sign of the radius while deriving the formula to be used on a consistent basis. And it is always better to substitute the radii and the image distance and the object distance along with the sign while solving the numericals. This happens to be a very important equation for to be used for thin lenses. Now herein one assumption that we have implicitly made is, again I am repeating that assumption, that all distances are to be usually measured from the pole, which is the center point. This particular point is the pole. But for the first equation that we have written over here, we have measured distances from this point P1, and for the second equation we have measured the distances from the point P3 instead of the point P2. So the implicit assumption that we have made over here is the fact that P1, P2 and P3 are almost coincident. This is the meaning of what we call as a thin lens. So when we are talking about thin lenses, the edge points of the lens, which are P1 and P3 over here, are going to be coincident with the pole of the lens, or which is the center point of the lens. That is the meaning of what we consider to be thin lenses. And this particular equation, it's to be borne in the mind that this particular equation is not for thick lenses. If the lenses are thick, then this particular equation will not be good, it will not be valid. We'll have to use the curved surface refraction formula twice. Also, while deriving the curved surface refraction formula, we have understood that this equation 1 and equation 2 holds good only for paraxial rays, that is rays that are close enough to the principal axis, that are not very far away from the principal axis compared to the focal distance, compared to f for example, or compared to r for example. So the paraxial ray approximation or assumption is already valid while we are deriving the equation of thin lenses. Okay, yeah. The sign convention, like I have remarked, should be utilized after using this formula, not before using this formula. So, and not during the derivation of this particular formula. Now, another third assumption that is implicit over here is the fact that here refractive index is mu1, here refractive index is mu2, and then again the ray is emerging onto the medium with refractive index mu1. Most often the refractive index of the outside medium is air, but in some questions it might not be so. In some questions also, the ray that is coming from the object might come from a medium having refractive index mu1, the lens might have refractive index mu2, and then the ray might emerge onto a medium which has refractive index mu3 for example, not mu1. So in such cases, here instead of writing mu1 again, we'll have to write mu3, and in that case the Lensmaker's equation will get modified. It will get modified as mu3 by final image V minus mu2 by intermittent image V1 will be equal to mu3 minus mu2 upon R2. So this is how the second equation will get modified. So the clouds are here for fun, and for like as a background. Yeah, they are a part of the background. So mu3 by V minus mu2 by V1 is going to be equal to mu3 minus mu2 divided by R2. Alright, and the first equation remains as it is. This first equation would remain as it is, which is mu2 by v1 minus mu1 by u is equal to mu2 minus mu1 by r1. So that is mu2 by v1 minus mu1 by u is equal to mu2 minus mu1 upon r1. So if we have a case wherein, okay, let's get rid of the prop, which are the clouds, for a moment because I need the space. Alright, so if let us say we have a scenario that goes something like this, that this is a lens and here mu1 is the medium, here mu2 is the medium, and here mu3 is the medium. Let's say if we have this kind of a scenario, then in that case we'll have to write down these two equations, and then we'll have to like formulate a different lens makers equation effectively for this lens. So it's going to be mu3 by v, by adding the two, it's going to be mu3 by v minus mu1 upon u, and this is going to be equal to, now let's understand, it's going to be equal to mu3 by r2 plus mu2 1 upon r1 minus 1 upon r2 minus mu1 upon r1. So let me continue writing it, minus mu1 upon r1. So this is the modified lens makers equation. So this concept might be applicable in some relatively sophisticated problems. It's not very commonly used, but I have mentioned it over here nonetheless.